Hi, folks. My name is Jan Kelly, and I work at Dalhousie University in the Department of Oceanography.
And my name is Jamie Harbin, and I also work at Dalhousie University.
And we're here talking about video 9. It's related to our argoFloats package. It's an R package. We're calling this one Advanced Quality Control. Maybe not that advanced, but it's just one step further to the previous video. And we'll begin. I'm going to stop sharing my screen in just a moment, but maybe I'll first quickly say the other browser in my window here is Hurricane Laura. So best of luck to everyone who is in the path of that hurricane. I think it'd be very, very bad down here, especially with COVID going on. So yeah, good luck to everyone on that. So now I'll stop sharing my screen, and Jamie will take over for a while.
Perfect. Okay, so there we go. So just as a reminder to everybody, this is where we left off during our video 8. So just again, as a reminder, the left plot here is before we used our apply QC function. And then the right here is after we use the apply QC function. And as we mentioned in the last video, you can see that there are still some points that are questionable or outliers. So essentially the point of this video is just to kind of look a little bit more in depth towards those points. So all I'm doing here, and again, all of my variables are already still defined and they're the same as video 8. So that's just kind of why I'm jumping into line 31 here. So line 31, I'm really just setting the margins just to look at one plot. And then line 32, I'm just focusing specifically on what we call clean, which is after the apply QC. So line 33, all I'm doing here is just defining SA, so absolute salinity. I'm just pulling out the absolute salinity within the clean Argo. And then I'm doing the same for the conservative temperature here. So we actually stumbled upon this function called identify. And what identify does is it allows you to interactively click on your plot, and it will tell you the position that the point of interest is at. So I should note, as you see in line 35, so it tells you to click on it, but sometimes because of this interactive nature, if you are to just source the code, on my computer anyways, it does crash RStudio. However, for whatever reason, when you go line for line, it does still work. So we are going line for line here, so we're good. So what I'll do is, so line 36, so you just define your X and Y, and this N equals 1 is just telling me identify that I'm only clicking one point. So I'm just going to click what we consider this outlier here, and it's telling me that it's at position 467. So all I'm doing here in line 37 is I'm saying that the bad absolute salinity is at the 467th position. And I'm doing the exact same thing again for the conservative temperature. And then line 39 is just kind of emphasizing that point there. And you'll see that pop up over on the right here. So now Dan has created this for loop, and he's going to take over here and just kind of explain a little bit as to what's happening.
Okay, but we're going to stick with Jamie's screen just to avoid the time wasting and popping back and forth. So in line 42, maybe you could make that one happen, Jamie? So what that's doing is it's grabbing out the Argos objects from the clean thing, and it's calling it cycles. And so that's now a list. Maybe, Jamie, if you could do a str of cycles, comma 1.
Sure.
And you see that it's a list, and it's got 9 things, and each of them is what's called an Argo object as defined in the OCE package. So argoFloats is sort of built on top of OCE. So what this loop is doing, and maybe don't do anything yet for a second, Jamie. What we're going to do is we're going to cycle along them. So seek along is going to be, that's going to create the integers 1, 2, 3, 4, 5 up to 9, and so that's going to be called iCycle or icicle, I guess, iCycle. So that's going to be an index. And then line 44 is going to grab out that version in this list called cycles. And then we're going to say, well, hang on, let's try to find, we're doing a which operation, and we're saying, is the salinity that we know to be bad, is that anywhere in this? And is the conservative temperature also in that? So if W has length 0, it means that it didn't find an exact match. But otherwise it will find a match. And so the if statement in line 46 is going to do that. So it's going to print a message. So maybe just make that loop happen, Jamie.
Sure.
So it ran through the loop. The other thing I forgot to say is that at line 50, it'll break. So when it finds the Argos in the list, when it finds the list item that holds the bad TS, it will break. So the graph that you see on the right there is all 10 of these TS diagrams all put together. And what we've just found from this, it's repeating the bad point. You see it in red in the bottom left thing. It's repeating the bad SA and CT, I'll say. And it's in the 7th cycle, index 7 of that list that we have called cycles. The cycle identifier is 147. So yeah, so 147. And it's at the 600 meters or 600 decibars below the surface. So what we've found there is that if we want, we can just look at cycle number 147. So should I pop back over to you, Jamie, and you can...
Sure, yep. So as Dan mentioned, all we're doing here now in line 55 is now, because of the for loop, we know that the cycle that we're interested in is cycle 147. So all we're going to do in line 55 is just subset our Argos type object for that specific cycle. And then we're just going to plot a TS of just that cycle. So you'll see that come over on the right here. And then what we're going to do, and we showed this in our last video as well, is we're actually going to do the show QC test. So determine which tests were performed and which were failed for that particular cycle.
Jamie, just before you do it,
Yep.
readers should, or viewers, or whatever they're called, there's some viewers, the imaginary viewers, look over in the TS diagram there, you can see that indeed we have retained that funny point there. And a person might be curious, there's other funny points, and a person might want to do what we just did, but clicking identify and some of the other funny points. And quite often you'll find them all in one cycle. I don't think that's the case here, but anyway, this just verifies the fact that we have that low salinity at a temperature of about 18 or something. Verifies that, yeah, we caught the right one. Okay, so sorry, Jamie, you could go back to what you were saying.
No, that was good. So yeah, as I was saying, so in line 57, we just were determining which QC tests were performed and failed. We're doing the style equals full so that it also tells us which tests were skipped, which we soon noticed that was actually really relevant for this particular profile or cycle. So I'll get Dan to explain a little bit kind of what the results showed us here.
Right. So there's a whole lot of tests that are done. These are done sort of, I would say, automatically. I mean, we didn't do them. So when you get data from the repository, there's a sort of identifier. We've talked about how this works, but there's an identifier within the data set that says what tests were performed. And to me, the very strange thing is that for a given float, we call it a float ID, but for a given float, it can happen that one cycle has a given set of tests and like 4 cycles later has different tests. And I think that must mean that a human has looked at them and been curious about one and just run some code and, you know, run some extra tests on that one and push it up to the server. I would have thought that they would all be processed together, but they seem not to be. Anyway, so the first one here, the test number 1 was skipped, platform identification test, skipped. It passed test number 2, which is an impossible date, like in the future or in, you know, 100 years ago or whatever. Number 3, impossible location, like for example, Milwaukee, probably no Argo floats there. Number 4, position on land, well, that was Milwaukee, wasn't it? I don't know what the difference between those is, to be honest. It passed the impossible speed test, and I presume that's just they look at the location and then 10 days later it's at a different location if that speed is works out to be 100 knots, then that's completely wrong. I'm speaking in like sailor terms, 100 knots, but I think you might know what that means. Then there's a global range test, which it passed. And I want to talk a bit about that. So this salinity there, I think, is weird for the temperature. If you look in the graph on the right, that salinity by itself, it's a little under 35, or whatever that's 35.3 or something like that. That's not strange. I mean, that's within the range of the salinities on that graph. The same for the temperatures, within the range of the temperatures as well. So there's no way that the global range test could possibly get those. Now, if you had a salinity of 2, the global range test would catch it, or negative, or 400, or something like that. But then there's a whole bunch of tests that were skipped here. Regional parameter tests, which again would be, this float is in a certain ocean, and we have certain ideas for its salinity and so forth. That was skipped. The pressure increasing test was skipped. That just says it should be descending. The spike test was skipped. That's the thing that says, is a point quite different to the points above and below it? That test was skipped. Well, I think if they had performed that test, Jamie, is there a chance you could move your mouse and circle around the point that I keep thinking about?
Yeah, for sure.
Yeah, okay. I would say that if they did a spike test, that would show up, because the one that was immediately above and below it was clearly in the rest of the cloud. So there was a real big jump in temperature and salinity compared to its neighbors. It's a shame that they didn't do that test. Top and bottom spike tests are always skipped, so we'll skip that. And the gradient test was skipped. Digit rollover test was skipped. Something did fail, the data inversion test, but this is an important point. This point that you're seeing has gone through and passed all of these tests. So it is not the case that that point failed the data inversion test. I honestly don't know how that quite worked. I'm pretty curious about that. Okay, but now I come down to test number 17. They skipped the visual QC test. I'm pretty sure that if anyone did a visual QC on this, they would have identified that as a problematic point. Right, so that was just kind of a walkthrough. I won't go through the rest of them. These are well documented in the Argo. Manuals is maybe 2 pages or so on each one, and if you were to try to code them up, they're each a page or 2 of code. There's a lot to it. It's not appropriate for me to try to summarize them here. Do we have any more code that we were going to show, Jamie?
No, Dan, I think that was everything. I think really the biggest point that this really shows is that as we shown here, that the user really is responsible for still, looking into their data and plotting things up, and really they're definitely responsible for that. So that's really all we want to kind of show here.
Well, that's good. Now, the other thing in terms of the future, I mean, we could do a video in which we alter the object and we find out well, I guess we already know the S and the T and the P. We could just change the flag there. I mean, we could change the flag from a whatever it is. Obviously, it's one of the passing things into a failing thing, and then save it. Now, what would the procedure be for an analyst? I think the best thing for an analyst to do is to start with data from the server, from the repository, and then modify them. So, I mean, a typical workflow would be that you would read them and you would find that for this particular cycle of this particular float, that you should change a flag there. It would only be 1 line of code. And, if you were working with hundreds of floats for the particular project you're working on, maybe every second one has a couple of lines that need to be visually fixed like this. And it really wouldn't be a problem. And of course, that identify function that Jamie was just showing is really a wonderful way of finding it. And I think watchers who are a little familiar with R would realize that it'd only be a couple of lines really to figure out how to ask the user. Just say to the user, if you think there are any bad points, click on them, and when you think you're done, double click on the left side or double click on this little button or something like that. And the code could then make those modifications and save them into a source file that would then get run to clean up the data. So we're talking about a investigator specific, not a float specific, but for your own project, that you yourself would fix up the data.
Exactly.
Now, another thing that we'll probably talk about pretty soon is using the adjusted fields, and maybe also, is that a thing that we have in mind for doing in the future, Jamie?
Yeah, for sure. We have no set date to it, but we definitely should talk about our use adjusted function within one of the videos.
Right, that's good. Okay, well, I think we've touched on the things that we were hoping to touch on. So I think I will say that for me, thanks for watching.
Thanks, everybody.
Bye.